So, about this project. I wanted a live avatar that could follow my face while still looking like a high-quality Blender render. Unfortunately, Blender and real-time rendering do not exactly go hand in hand. So, I come up with a perfectly reasonable solution.
You did not.
So I decided to make an AI do Blender's job without waiting an eternity for path-traced image. Okay, so generating a single Furry image is relatively easy. All you need is a 3D model and a few minutes. Unfortunately, in Blender, we measure performance in seconds per frame, not frames per second. And what I really wanted was speed. Real-time speed, to be precise. And we will not be able to achieve this with Blender cycles. But there is one technique that might fake high-fidelity results and render fast enough. You may heard about some of the nasty things Nvidia has been doing lately. That got me thinking. Maybe I could do something similar. Nvidia has supercomputers, and I have a 5-year-old GPU, Blender, and Optimism, and one of these resources will soon disappear. Unfortunately, real-time neural renderers is not something easy to achieve. At this point, I am expected to explain machine learning in 80 seconds, upsetting both engineers and people who enjoy accuracy. Fortunately, other people have already done this properly. Links are in the description. But to understand this project, I would like to explain to you a few things. So first, dataset is a collection of examples for the model to train on. In case of stable diffusion, each has an input, the number describing my face mockup data, and a target that is rendered Blender image. A model is a diffuser. Big machine learning model that receives an input and makes a guess. Initially there is impressively bad, but by minimizing the loss function, we can make it do anything we desire. The loss function compares the guess with the correct answer and turns the difference into a scalar. Training adjusts the model's weights to make that number smallish. Sometimes we can get creative with the loss functions. More about this later. MediaPipe converted my face into 52 expression values and 6 numbers for head rotation. This gave the computer enough data to recognize all my expressions. With simple Blender script, I can convert these values into animation in Blender and render it normally. So Stable Diffusion already knew what a furry character looked like. Unfortunately, it did not know how my character looks like, which is a very important piece of information for a project like this. Also, this checkpoint contains enormous amount of patterns that might be important generally, but are unnecessary in this scenario. So I could fine-tune the whole network, but that would mean changing hundreds of millions of parameters just to explain green eyes, spots, jacket, fur, that fur. This is probably even impossible on my setup, as it would require gradients for the whole network, and that would not fit into my VRAM. Instead, I can use a technique called LoRA, low rank adaptation. It was originally developed for language models, but people quickly discovered that it was useful for almost everything else too. So instead of training another gigantic matrix, I only train 2 small skinny ones. This low rank limits what can change, but for teaching an existing model one new thing, that's usually enough. So the original network stays frozen, and one LoRa matrix compresses the signal through a thin bottleneck, and other expands it again. And this product becomes a correction to the original activation of the layer. In my first test, this meant almost 800,000 trainable parameters. That sounds large until you put this next to the full network, which is 1000 times bigger. To steer the diffusion model, we usually use text input. Normally, prompt is converted into a conditioning vector using model called clip, and fed throughout the network to inform it what kind of output we want. In our case, the text input is useless, but the output of the clip is just a vector. And mockup data is basically same kind of vector. So by feeding it through adapter, model can learn what the mockup values represent and reflect it in the image. The first results looked right, as long as I did not try to animate it. So apparently, diffusion models are very bad at temporal stability. They may generate images that are technically correct, but when we put them together, we will notice that animation is not playing nicely. Every generated frame had the same problem. It had not a good way of knowing what have come before it. And there is one unfortunate, ungodly creation that might solve our problem. And it is called recurrent neural network. And it is called recurrent neural network. Recurrent neural networks are feeding their previous outputs as their inputs. And I really do not like working with them. But sometimes they can get stuff done and I need to not be picky. But memory alone is not enough to solve temporal stability problem. We need to explain to the model how to use information from previous frames. And we can do this by adding temporal loss. The definition might look scary, but the idea is simple. It checks whenever the generated image changes in the same way as the real image. With this, we can enforce the same amount of movement as there was in original. Diffusion models are very chunky, and they work in multiple steps. I tried to compress the model into a small network using a process called distillation, but it all failed because I had too little compute to train small model. But about the steps. Instead of 20 careful corrections, the model had to make one extremely well-educated guess. And this one step has to be big. And this task is an order of magnitude harder. I tried to make this as easy for the model as possible by carefully preparing the initial state, but still, with one try, the guess will create a blurry mess. And that's because blurry image can be numerically pretty close to a sharp one. And it is a lot safer guess for standard latent loss function. This kind of behavior is very much against the Furry, or details in general. So with some research, I found few techniques that might help with that. But first, one quick note. Stable diffusion does not work directly with the RGB pixel image. It first compresses it into a smaller grid of numbers called latent. A latent is the model's compact internal representation of the image. You can see this here. First, latent reconstruction compares the predicted clean latent with the latent encoded from the Blender target. It cares about the pose, color and overall structure. With this, we can make sure that the pose is correct and the model knows the character. But also this is the source of blurry details, because in case of latent loss, average is a good enough answer. So now, let's focus on losses that actually improve quality. Sobel light gradients measures how quickly the image changes horizontally and vertically in latent space. So boundaries around full eyes and silhouette become visible while flat areas mostly disappear. The Laplacian compares each location with its neighbors and responds when the center changes sharply in any direction, making small texture and thin details easier to detect. We optimize the average magnitude of these maps so that both source and predicted image contains similar amount of details. But we do not require pixel perfect alignment. It makes model prefer sharp images over blurred ones. Third, local frequency loss moves the compression into the frequency domain and focuses on the frequencies that the model reconstructs badly. A Fourier transform describes the image as the mixture of spatial frequencies. Low frequencies represent broad shapes and color changes, while higher frequencies contain finer texture and edges. This discourages the model from producing only smooth low-frequency shapes while ignoring the texture needed for the fur. Finally, high-frequency temporal loss checks whenever fine details change consistently with the real Blender sequence. First, we calculate the change between two generated frames and the change between target frames. Then we compare their gradients and Laplacian details. The loss penalizes extra sparkling, disappearing edges and texture changes that are not present in the target. It does not demand that every strand must remain on the same pixel. It demands that the generated detail changes consistently with the source sequence. And after a while, and with these losses, the results are quite good. Head follows the movement, HAL expressions are reproduced. There is some bias towards expression enforcing head position, but this is a very minor issue. Overall, results are pretty satisfactory for the model trained only for a few days on a single GPU. There is still one issue. Even though we moved from seconds per frame to frames per second, the performance is still not good. This diffusion model runs at only few frames per second, and I like more frames per second than a PowerPoint presentation. Fortunately, NVIDIA is here to help. It has a tool called TensorRT, which is a very powerful optimizer for neural network. It takes a trained model as a graph of operations, then it builds a version made for one specific GPU. First, TensorRT cleans up the graph. It joins operations that can run together. It avoids setting a temporal resource when they are not needed, and it also can use faster 16-bit numbers. Then it chooses how each operation should run. The same job can often be done in several ways. For example, it can calculate the same convolution using different algorithms. The same is true for matrix multiplication. Different kernels can produce the same result, but some are faster than others, usually with trade-off in memory usage. TensorRT calls each operation a tactic. While building the engine, it tests the tactics on a real GPU. Testing more options makes the build take longer, but the finished engine may run faster. In my RTX 3080 test, Dagger managed 5, maybe 6 FPS. TensorRT reached more than 14 FPS. That's almost twice as fast. And on RTX 5090, the TensorRT reached almost 30 FPS, but that GPU is a beast. Of course, the engine solves only the neural network part. A complete Furry webcam needs much more. And those were my final tests. Thank you for listening. I hope you enjoyed this project.